This lesson on free energy along with Gibbs free energy of chemical reactions. We're going to start with a couple of equations that came up already. Delta S of the universe is equal to delta S of the surroundings plus delta S of the system. We're going to replace our delta S of surroundings with negative H over T. We had that from last class. Negative delta H over T plus delta H of the system. So when we replace that, we're going to multiply through by a negative T, get rid of fractions. Negative T delta S of the universe equals delta H minus T delta S. Since the only S we have now is a system, we're going to ignore the subscript S of YS. So everything's in that. And this equation here is also known as delta G, or Gibbs free energy. A word of warning, delta H is commonly given to you in kilojoules, whereas delta S is in joules per Kelvin. So sign changes needs to be alert. What we're going to do is calculate delta G for water melting at 3 different temperatures. Delta H for water melting is 6.03 kilojoules. So that's delta H minus T. The temperature we're going to use is 263, and delta S is 22.1 joules per Kelvin, so that's 0.0221 kilojoules per Kelvin. Kilojoules, now we're in kilojoules. And that will give you a value of 5.81 a positive or negative. A positive 5.81. So it's not spontaneous because delta G has to be a positive number. So this is a negative number. So this is a positive, and at temperature less than 10 degrees below zero, ice does not melt. So kilojoules. Same setup, only we're going to bring it up to the temperature of melting ice, 273.15. And everything else is the same. They're in kilojoules. This turns out to be darn close to zero, which means at equilibrium. If you have ice, water at 0 degrees of equilibrium, raise the temperature up again to 283. Kilojoules, you're going to end up with a negative. You got to subtract there. That's what I forgot to do. So that minus that is a positive 0.15, 0.19. Subtract those two guys, and you're going to get a negative 0.22 kilojoules. Again, it's the sign that we're really interested in. A negative delta G means it's spontaneous, irregardless of temperature. And this is the ultimate standards that we want to do. One other situation is, if you know the delta H and delta S, what would be the temperature at equilibrium? In other words, words, when does the reaction stop or start proceeding? 0 would be that temperature, that delta G that we want. And let's say it's negative 3,000 joules, negative 3 kilojoules, minus T delta S, which is 15. Do the math and you get the temperature of 200 Kelvin. So at 200 Kelvin, the reaction stops being spontaneous or starts being spontaneous, depending upon what sign you're looking at. Same situation here, except 3,000 joules minus T15. Here, the delta H is a positive number, so if you subtract, you're going to get a negative. I'm going to do this backwards. This is going to be actually negative 200 Kelvin. Kelvin cannot be that, so there's no, it will never be spontaneous or always be spontaneous, depending upon what the signs are. This one, you subtract 3,000 and you get divided by negative 15, and T equals positive 200 Kelvin. So that means at 200 Kelvin, the reaction will stop proceeding. A little bit more about entropy as it applies to a chemical reaction. You can define S, entropy itself, as a perfect crystal at 0 Kelvin. No such things exist, because you cannot get absolute zero. But if you could do that, then that would be the S of a perfect crystal. So if you have any tiny flaws or any temperature slightly above 0 Kelvin, it will not be a perfect zero. This is also known as the third law of thermodynamics. As far as the chemical reaction goes, if you can predict whether a reaction has increasing entropy or not, if a chemical reaction produces more gas particles, that means add the coefficients of all the gas particles, then you're going to have a positive delta S. If you're going to produce fewer gas particles, some of their coefficients, you're going to have a negative delta S. If that's the same in all cases, then you go to more liquid / solution. Then you have a positive delta S. If you have two solids mixed together that makes a liquid, then the entropy is increasing that way. If you have a small, simple molecule to a more complex molecule, then your entropy will increase. Think that if you have a binary molecule, there's only one way that happens, that it can be arranged like that. If you have a more complex molecule, you can go like that, make it M. You can twist things around, up, sideways, down. So 1, 2, 3, 5, 1, 2, 3, 4, 5. So the more complex molecules there are, the more ways they can twist around and spin and rotate things. So that increases your entropy. So if you are to predict via a chemical reaction, this is how you would do that. You can also calculate delta S using tables, just like you did last semester with delta H formation. In fact, it's on the same appendix tables. So the second column is the first column. If you have coefficients, you multiply them. So if you have 3 PO2 making 2 P plus 3 O2s, you would switch the sign on this side and double whatever the same signs, but you keep them up and add them up. This is very, very similar to what we've done in the past. Same deal if we have to calculate delta G, which is the next section. There are 4 ways of doing this. Absolutely none of these ways is different from what you've had already. First way is use Gibbs free energy equation. Delta G equals delta H minus T delta S. Given or find, calculate delta H and delta S. You can, from a table, just like you did with delta H and delta S up here, if it's a coefficient, you multiply it. If it's on the left-hand side, you multiply negative, so it's a negative coefficient of the value, plus dot, 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 plus the coefficient of the value, dot, 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 and you total them up to get to the sum. 2B is using the table again, except you got to calculate delta H by the above method and delta S by the above method. Then use delta G equals delta H minus T delta S. And the third way is using Hess's law, where you have equations you gotta flip, rotate, double, take half, manipulate the steps of reaction to come up with the net reaction that you got. And this is lesson on free energy.